Hello, welcome to this lecture on thermodynamics. In this lecture, I am going to discuss few multiple choice questions from thermodynamics part. Okay, let's move on to the question number 1. All spontaneous processes are, four options are given: reversible, irreversible, reversible adiabatic and adiabatic. Actually, there are several statements of second law are available. Okay, statements of second law of thermodynamics. There are several statements available. This is one of the important statement that all spontaneous processes are irreversible in nature. All spontaneous processes are irreversible. It's a direct statement. It's one of the statement of second law of thermodynamics. Okay, so all spontaneous processes are irreversible. So the correct option for this question is option B. Option B. Okay, and remember this additional information: for reversible process, for any reversible process, okay, change in entropy, total change in entropy or change in entropy of the universe should be greater than 0. What does this indicate? Entropy has to increase. Total entropy has to increase. Yes, in all natural processes or in all spontaneous processes, total entropy means entropy of the system plus entropy of the system surrounding. The total entropy change must increase, or total entropy must increase. Okay. In the case of reversible process, for reversible process, change in entropy of the universe is equal to 0. What does this indicate? For reversible process, entropy remains constant. Okay, so keep this point in mind, very, very important. But for this question, the answer is direct. All spontaneous processes are irreversible in nature. So the correct option for this question is option B. Okay, right. Now let me move on to question number 2. Right, this is question number 2. Cp equal to Cv for a fluid. 4 options are given here. Cp equal to Cv for a fluid. We need to identify the correct answer for this. First, go through the options. Cp equal to Cv for a fluid. See here, the word fluid indicates, what is meant by fluid? Fluid means liquid or gas. Liquid and gas, okay, they are combinedly called as fluids, right? When Cp and Cv are equal for a fluid, option A, Cp equal to Cv for a fluid which is compressible, Cp equal to Cv for a fluid which is homogeneous, Cp equal to Cv for a fluid whose volume coefficient of expansion is negligible, Cp equal to Cv for a fluid under normal temperature and pressure. So these are the 4 options given. Now, first let me give you what is the general expression for Cp and Cv. We know very well, Cp minus Cv is equal to T into C. It's an easy method to remember this. So we have pressure here, volume here, okay, and PVT are the 3 important state functions which need to be which will give you the equations of state. Okay, so we have pressure here, we have volume here, which is left temperature. So put temperature first. Then we have to differentiate volume with respect to temperature, keeping pressure constant. Then differentiate pressure with respect to temperature, keeping volume constant. Okay, this is an easy technique to remember. Okay, now when Cp and Cv become equal, observe this carefully. If right hand side is equal to 0, then Cp minus Cv equal to 0, you will get Cp equal to Cv. Right? Under what condition right hand side becomes 0? Either temperature should be 0, or this is expansion term, right? At constant pressure, if you change temperature or if you increase temperature, right, volume will increase. Or by keeping volume constant, if you increase temperature, pressure will increase. So I have three terms here. If any one is 0, automatically the right hand side becomes 0. Now I will go through the first option here. Cp equal Cv for a fluid which is compressible. Compressible means, right, compressible means by increasing pressure, okay, we can change the volume, right? But we don't have that term here, right? Therefore, this right hand side never becomes 0 for as per as option A. Then let me go to option B, which is homogeneous. There is no term related to homogeneous here, right? So you need not worry about option B also, right? Cp equal to Cv for a fluid which is homogeneous. This is wrong, right? Then see option C, whose volume coefficient of expansion is negligible. Okay, what is meant by volume coefficient of expansion? Volume coefficient of expansion. It is usually denoted by the symbol alpha. Alpha is equal to 1 by V into dou V by dou T at constant pressure. This is what we call as volume coefficient of expansion. See here, if this becomes negligible, negligible means roughly 0. If dou V by dou T at constant pressure become negligible, right? Yes, I have this term here. See here, dou V by dou T at constant pressure term is there. If this is negligible, then volume coefficient of expansion become negligible. I'll say in the other way. If this value is negligible, then volume coefficient of expansion become negligible. So if this value is negligible, negligible means 0. If I put this value 0, then right hand side becomes 0. If right hand side becomes 0, then Cp becomes equal to Cv. Okay, so Cp and Cv becomes equal. Cp and Cv becomes equal, right, when the volume coefficient of expansion is negligible. So the correct option for this question is option C. Now let me check the option D also. Under normal temperature and pressure, see, this right hand side becomes 0 if temperature becomes 0, but it is given normal temperature, it is not 0 actually. Therefore the right hand side never becomes 0 even for the option for option D also. Okay, so the only option for which the right hand side becomes 0 or negligible, right, is option C, whose volume coefficient of expansion is negligible. Okay, therefore the correct option for this question is option C. Note down. Cp equal to Cv for a fluid, okay, is possible, right? This is one of the possibility if volume coefficient of expansion is negligible. If temperature is 0, yes, then also Cp becomes Cv. Cp becomes equal to Cv. Okay, right, next. Now let me move on to the next question. Question number 3. Chemical potential is, 4 options are given: an extensive property, an intensive property, a path property, a reference property. Okay, observe this carefully. We know very well Gibbs free energy G for n mole of gas, for n mole of a pure substance, any pure substance, right? It is an extensive property. Observe carefully, because it depends on number of moles. As number of moles increases, yes, Gibbs free energy also increases. So Gibbs free energy for n mole of a pure substance. Pure substance means it should not be a mixture. Okay. So pure water, pure oxygen gas, pure nitrogen gas, right? That's the meaning for pure substance here. For pure substance, okay, Gibbs free energy depends on number of moles. As number of moles increases, Gibbs free energy also increases. So Gibbs free energy is an extensive property. Whereas if I divide Gibbs free energy by number of moles, what we get? We get Gibbs free energy. If I divide Gibbs free energy for n mole of gas by number of moles, I'll get Gibbs free energy per mole. Gibbs free energy per mole of the substance. Okay. In the case of pure substance, yes, this is nothing but chemical potential. And Gibbs free energy per mole, right? It is an intensive property. So chemical potential is an intensive property. It does not depend on amount, because we take Gibbs free energy for 1 mole. Gibbs free energy per mole is nothing but chemical potential, right? Therefore, it is independent of amount. It is an intensive property. Okay, whatever amount you take, but we are going to measure chemical potential for 1 mole only, right? So chemical potential is an intensive property. So the correct option for this question is option B. Chemical potential is not a path property, because chemical potential is nothing but Gibbs free energy per mole. Gibbs free energy is a state property. So chemical potential is also state property. It is not a path property. Then it is given it is a reference property. It is wrong. Okay, reference means we have to keep pressure as 1 bar. Okay, so it is not a reference property here, right? Chemical potential is a state dependent property, right? And chemical potential is an intensive property. So the correct option for this question is option B. Okay, then let me move on to the next question. Question number 4. Which one of the paths correspond to an isothermal reversible process? See here, a graph is given where in the y-axis we have temperature and in the x-axis we have pressure. Okay. So in this, a system is moving, or an operation is carried out, or a thermodynamic process is carried out such that the system is moving from state 1 to state 2. And different paths are given. You can change the state from 1 to 2 through path A, or through path B, or through path C, or through path D. There are 4 paths are given. The question asked here is, which one of the path, 4 paths are there, which one of the path corresponds to isothermal reversible process? Isothermal means temperature should be constant. See here, temperature is in y-axis, right? In path A, right, whatever point you take along the path, whatever point you take, the temperature is same. The temperature remains same. Whereas in path B, see, as we go above and above, at this point we have one temperature, at this point we have a different temperature. Temperature is changing. So if you see path A or path D, in all these paths except path A, in all other paths, temperature changes as the process begins, or as the process progresses. Okay, so the only path in which temperature remains constant is path A. Okay, if temperature remains constant, we call that path is isothermal path. Okay, so if temperature remains constant, then the path is called an isothermal path. Isothermal path. And it's a standard procedure that suppose if we have if you plot temperature versus pressure, or pressure versus volume, and if system goes from state 1 to state 2, we represent reversible process by solid lines like this. If a path is given as solid line, it is a reversible path. It's a reversible process. For irreversible process, the standard method of representation of irreversible process is dotted lines. If we put dotted lines, that indicates an irreversible process. So here all paths are given in solid line, so all the paths are reversible as per standard convention. Okay, but only along path A temperature remains constant, so path A is an isothermal process. Okay, yeah. So the correct option for this question is option A. Right, now let me move on to the next question. Question number 5. Question number 5. Just go through the question. The unit of isothermal compressibility is. Unit of isothermal compressibility is. What is isothermal compressibility? Those who are preparing for PG TRB examination or assistant professor TRB examination, okay, try to remember these two, which is very important. One is alpha, the other one is beta. In some book it is given as kappa. Okay, what is alpha? Alpha is nothing but coefficient of thermal expansion. Coefficient of thermal expansion. Okay, or coefficient of isobaric is a even perfect term. Coefficient of isobaric thermal expansion. What is the formula? The formula is this 1 by V, which I gave already, dou V by dou T at constant pressure. Keep pressure constant, it is isobaric, and change the temperature, so volume changes, that is thermal expansion. Then what is beta? Beta is nothing but isothermal compressibility coefficient of. Beta is the coefficient of isothermal compressibility. Okay, so what's the formula? The formula is this minus 1 by V into dou V by dou P at constant temperature. This is the expression for isothermal compressibility, coefficient of isothermal compressibility. Now, in the question they have asked the unit of isothermal compressibility. So they are asking unit of beta. Okay, what is the unit of beta? Let me do it here. It's very simple. For beta, unit is, listen, don't worry about the minus sign and all, just see the units of the variables, okay, or units of the terms that is available here. So volume, is 1 by meter cube. Okay, 1 by, I have 1, volume is the denominator, so meter cube, and in the numerator dou V, which is meter cube, and in the denominator here we have pressure unit is Pascal. Okay, meter cube cancels here. Okay, therefore 1 by Pascal, or you can write Pascal inverse. Okay, so the unit of isothermal compressibility is Pascal inverse. Similarly, so the correct option, because they are asking unit of isothermal compressibility, so the correct option is B. Okay, similarly, what is the unit of, this is unit of beta. Similarly, what is the unit of alpha? Coefficient of thermal expansion. Right, I have 1 by V here, so 1 by volume unit is meter cube, SI unit. Then we have dou V, change in volume, unit is meter cube. And we have change in temperature, unit is Kelvin. Meter cube cancel here, so the unit here is Kelvin inverse. So unit of alpha is Kelvin inverse, unit of beta is Pascal inverse. Remember both the units. Okay, and remember these two expressions, which are very, very important. Okay, and one more point, alpha and beta, these two can be determined experimentally, right? So apart from pressure, volume, temperature and heat capacity, Cp, Cv, right? Alpha and beta are other two terms which can be measured experimentally. Okay, so which are all the quantities are experimentally measurable quantities, right? Keep this in mind. Okay, now let me move on to the next question, question number 6. Just go through the question. Identify the incorrect options among the following. 4 options are given: cyclic integral of change in volume, cyclic integral of change in volume, cyclic integral of change in work done, cyclic integral of change in temperature, cyclic integral of change in enthalpy. Yeah, this is also a direct question. See, we know very well that cyclic integral, okay, this is one of the property of state functions. Cyclic integral of change, D means change in any state function or any function. Let me write like this: cyclic integral of, okay, integral, this cycle symbol indicates cyclic integral of change in any function. If it is 0, then that function should be a state function. This is one of the important property of state function. Okay, if cyclic integral of change of any function, right, if it is 0, then that function should be a state function. Now just go through the options. In option A, I have cyclic integral of change in volume. Yes, volume is a state function. Yes, since it is a state function, this cyclic integral change or the total value of this should be 0. Yes, this is correct. But they are asking the incorrect option. Observe this, observe the question carefully. In the second option, work done is given. Work done is not a state function. It is a path function. For path function, cyclic integral of change in work done is not equal to 0, but it is given equal to 0. So for this question, the correct option is this. We also check the option C. In option C, yes, temperature is there. Temperature is a state function. In option D, we have enthalpy. Yes, enthalpy is a state function. Okay, so pressure, volume, temperature, internal energy, enthalpy, entropy, Gibbs free energy, Helmholtz free energy. These are all examples for state functions. State functions. For state functions, cyclic integral of change in state function should be equal to 0. But W, work done, is a path function. For path function, cyclic integral is not 0. Okay, so cyclic integral of, okay, change in work done is not equal to 0. Similarly, cyclic integral of change in heat transfer or heat transferred in a cyclic process. Okay, what is the total heat transfer in a cyclic process? That is also not equal to 0, because W and Q, work and heat, are path functions. Okay, yeah. So for this question, the correct option is B. Now let me move on to question number 7. Which, just go through the question. Which among the following is correct for an isolated system? Del Q equal to 0, del W not equal to 0, del Q not equal to 0, del W equal to 0. Okay, in all the options, del Q and del W are given. Okay, what is del Q? Del Q is nothing but small amount of heat transferred, infinitesimal amount of heat transferred. Heat transferred in a process. What is del W? Small amount of work done. Small amount, very small amount, infinitesimally small amount. Small amount of work transferred in a process. Okay. Remember, the system given is isolated system. Isolated system. What is isolated system? Isolated system is one in which, okay, no energy transfer, no mass transfer takes place. No mass transfer, no mass transfer, and no energy transfer takes place. Energy transfer. So now see this. Energy transfer means all forms of energy. Whether it is heat energy, so the heat transfer, right, should be equal to 0 for an isolated system. No heat energy transfer, right? So heat transfer never happen from system to surrounding or surrounding to system. Actually speaking, in isolated system, okay, there is no interaction between system and surrounding. Actually, we say that in the case of isolated system, right, system is the universe. System is nothing but universe. Right? Here, usually what we say, system plus surrounding is universe. But in the case of isolated system, system itself is called universe. Okay. So there is no energy transfer. That means heat is also energy. So it is not that transfer is zero. Similarly, work transfer is also zero. Work also a form of energy. Okay. There is no expansion or compression of gas takes place in isolated system. In isolated system, volume should be constant. In isolated system, volume should be constant. Okay. If volume changes, expansion or compression changes, then work will occur. Right? It is given clearly no energy transfer. No energy transfer means any form of energy. Right? Even work is also a form of energy. So del Q and del W should be 0. Right? For an isolated system. Since these two are 0, according to first law, change in internal energy equal to del Q plus del W. Since del Q is 0, del W 0, du also 0 for isolated system. For isolated system, change in internal energy also 0. Okay, keep all these things in mind. Now, keeping this information in mind, just go through the options. In option A, del Q 0 is correct, but del W not equal to 0 is given. Similarly, just go through all the options. Yes, it is very clear. In option D, del Q and del W both are 0. So this is the correct option. For isolated system, both del Q and del W should be 0. Okay? Yeah, this is question number 7. Now, let me move on to question number 8. Yes, go through the question. Question number 8. Delta H is equal to integral of Cp into dt is valid for. Delta H is given. So, you know very well. Enthalpy is a function of temperature and pressure. Temperature and pressure are convenient variables. So that's why I have taken temperature and pressure. Therefore, if there is any change in enthalpy, right, then the change may occur due to change in temperature or the change may occur due to change in pressure. So, how change occurs due to temperature? Change in enthalpy due to change in temperature at constant pressure into dt. So this will give you change in enthalpy due to change in temperature plus change in enthalpy due to change in pressure keeping temperature constant into dP. This term will give you change in enthalpy due to change in pressure. Okay? Yeah. Now observe this carefully. Here it is given delta H is equal to Cp into dt is valid for. Option A is valid for ideal gas, valid for real gas under isothermal process, valid for real gas under isochoric process, valid for any gas at constant temperature. Listen carefully. First, I'll just go through option D first. Any gas at the constant temperature. If temperature is constant, okay, let me take one more step here. dH equal to dou H by dou T at constant pressure is nothing but Cp. So Cp into dt plus dou H by dou P at constant temperature into dP. Now, see option D, any gas, it is valid for any gas at constant temperature is given. If temperature is constant, dt becomes 0. If dt becomes 0, then Cp dt becomes 0. Then you will never get this value because Cp should be there. Therefore, option D cannot be the correct option. Now let me go to option C. A real gas under isochoric process. Isochoric means volume should be constant. If volume is constant, then see dt is not 0, dP is not 0. Therefore, both the term will be there in delta H. But in delta H, I have only Cp into dt. This term is not there. Okay, this term never becomes 0 because we are keeping volume constant. Isochoric means volume constant. But I have pressure here. Okay, so if volume is constant, both the terms should appear in dH. So if you take delta H, you will get this term as well as this term. but according to this question, only this term should be there. Therefore, option C also wrong. Now let me go to option B, a real gas under isothermal process. You take a real gas, but it is given isothermal. Isothermal means temperature constant. If temperature is constant, then dt becomes 0, then this part becomes 0. If this part becomes 0, then you will get a wrong answer. So this is also wrong. Now let me go to an ideal, option A. In option A, ideal gas is given. Observe carefully. Here, they didn't mention whether temperature is constant, pressure constant, volume, nothing is there. It is given simply ideal gas. But we know very well for ideal gas, okay, internal energy is a function of temperature only. Also, enthalpy is a function of temperature only. Very, very important. It's a function of temperature only. So in this expression, see here we are keeping temperature constant. If temperature is constant, okay, if temperature is constant, then change in enthalpy becomes 0. So if temperature is, see, enthalpy depends only on temperature. If temperature is constant, then this change in enthalpy becomes 0. So for an ideal gas, dou H by dou P at constant temperature becomes 0. Since this becomes 0, this entire part becomes 0. So what we get is dH equal to Cp dt. This is dH. What is delta H? Delta H nothing but integral of dH. So nothing but integral of Cp into dt. Are you able to follow? So for ideal gas, irrespective of the condition, whether isobaric, isochoric, whatever it is, for ideal gas, right, whether pressure constant or volume constant, okay, this is the only formula. Delta H is equal to find delta H. Delta H equal to integral Cp into dt. So the correct option for this question is option A. Right? Then let me move on to the next question. Question number 9. Yeah, what is question number 9? See here. The coefficient of thermal expansion of an ideal gas equals to coefficient of thermal expansion alpha. You know very well. For ideal gas, what's the value of alpha they are asking? Okay. Yeah. You know very well alpha is nothing but coefficient of thermal expansion is 1 by V into dou V by dou T at constant pressure. Okay. First I will find out this quantity for ideal gas. For ideal gas, you know very well PV equal to nRT for ideal gas. All ideal gas obey this equation, PV equal to nRT, right? We want V here, so keep V as such, nR by P into T. I can write like this. Now what I have to do? We have to differentiate V with respect to temperature, keeping pressure constant. So keeping pressure constant, N number of mole is already constant, R is constant. Now we have to keep pressure also constant. So nR by P is a constant now. Now differentiate V with respect to temperature, keeping pressure constant. What we get is, since nR by P is constant, keep it as such. If I differentiate temperature, we'll get 1. Okay, so nR by P is the value of this quantity. Substitute this quantity here. For ideal gas, alpha is equal to 1 by V into, in the place of dou V by dou T at constant, I'll substitute this here. So nR by P. Okay, so alpha is equal to nR by P into V. As per ideal gas equation, what is PV? PV equal to nRT. Therefore, I can write this as, keep the nR as such. Instead of PV, I'll put nRT. So this nR cancel. So alpha is equal to 1 by T for an ideal gas. Okay, coefficient of thermal expansion is just 1 by T for ideal gas. Okay, take down. Right. Similarly, what is the coefficient of thermal compressibility? Okay, let me do it in the next page. Coefficient of compressibility. See beta. Right? Beta is equal to minus 1 by V into dou V by dou P at constant temperature. Isothermal compressibility, coefficient of isothermal compressibility. right? Yes, what's the value of beta for ideal gas? And ideal gas, you know very well, PV equal to nRT. We should keep volume as such, volume equal to nRT by 1 by P. I'll write like this. Okay. Now here we should keep temperature constant. So nRT, all these three are constant now. I'm going to differentiate V with respect to pressure, keeping temperature constant. So keep nRT as such, it's a constant. If I differentiate 1 by P, I'll get 1 by minus 1 by P square. Okay, you know very well, differential of 1 by X is minus 1 by X square. So 1 by P, if you differentiate, you'll get minus 1 by P square. Okay, substitute this value here. Therefore, beta is equal to minus 1 by V into minus nRT by P square. Okay, minus and minus become plus. So plus nRT by, here I have P square, I'll separate P square as P into P. Okay, so I'll keep 1 P as such, then P with V I can write PV. As according to, for ideal gas, PV is equal to nRT, therefore nRT by P into nRT. This nRT cancels, you will get 1 by P. So for the coefficient of isothermal compressibility, beta, that is beta for ideal gas is 1 by P. Okay, alpha is 1 by T, beta is 1 by P. Okay, yeah. Then let me move on to the next question, question number 10. The canonical variables for enthalpy is, okay, for enthalpy, what are the canonical variables? It is very easy to find this. Try to remember these 4 equations. These are all called fundamental equations of thermodynamics. Change in internal energy du is equal to TdS minus PdV. Then change in enthalpy is equal to TdS plus VdP. Change in Gibbs free energy equal to VdP minus SdT. Change in Helmholtz free energy equal to PdV minus SdT. All these 4 equations are applicable for closed systems. Closed system and pure substance. Closed system containing pure substance. For this you can use these 4 equations. Now we need to find canonical variables for enthalpy. So I'll take enthalpy. Listen, enthalpy, the change occur due to change in entropy and change in pressure. So entropy and pressure are called canonical variables. Entropy and pressure are canonical variables for enthalpy. Right? Similarly, for internal energy, okay, for internal energy, canonical variables are entropy and volume. Okay. Similarly, for Gibbs free energy, the canonical variables are pressure and temperature. For Helmholtz free energy, canonical variables are volume and temperature. Here we have volume, here we have temperature. Okay. So the correct option for this question is option C. Right? Yeah. I find that the discussion of these questions, right, will definitely give you some basic idea on thermodynamic topic. Okay, I stop here. I'll come up with a few more questions in the next lecture. Thank you all.